All right, so in this video, I'm going to try to go over pretty much everything you need to know about logs, about logarithms for the analysis SL test. And obviously, I'm not going to be able to hit on every possible way of asking the question, but I'm going to hit the big things and try to go over it. If there's something in here that you don't understand, just ask. I'll add on to it. So here's the big idea. Sometimes we have equations that we want to solve, and so we make up something that can solve it. Make up a new thing that can solve the equation. And we call that new thing an inverse. And what an inverse is it's the thing that undoes the operation that's in the equation. So if I start with a real simple example, x plus 5 equals 2, the inverse of plus 5 is minus 5, right? And so that solves the equation, and that gives me x equals negative 3. If I had an equation like x to the fifth power is equal to 32, we make up an inverse, and that inverse is the fifth root, or you could do the 1/5 power, and you would get that x is equal to 2. Most operations have some sort of an inverse that we can write down, and log is no different. If I have an equation like 5 raised to the x is equal to 125, the inverse that I apply to both sides is log with a base of 5. Okay? So, what I want to talk about here is when you have plus in the original equation, your inverse is minus. That's something that we all know. We learned that back in elementary school. When we have x raised to the fifth power, we do the fifth root. That's an inverse that most people are fine with. They know that a root will get rid of the power. Logs are what you use when you need to cancel out the base of an exponential problem. So log base 5 is the inverse that cancels a base of 5 in an exponential problem. So when do you use logs to solve equations? You use them when your variable is up in the exponent. Okay? Now, if you are asked to do this on paper 1, you're going to have to do it with no calculator. And so you need to remember that it's an inverse. So the same way that we talked about subtracting, if I think of 2 minus 5, I can think of that as the question, what number plus 5 makes 2? And the answer is negative 3. Same idea. If I do the fifth root of 32, I'm asking what number to the fifth power is equal to 32, and I get an answer of 2. So if I'm doing this problem here with log base 5, I'm saying what power of 5 is 125? The log is the inverse of the exponential function, and so instead of knowing what the power is, it's asking what the power is. So it's saying log base 5 at 125 is saying what power of 5 is 125. And so you get an answer that x is equal to 3. So if it's on paper 1, you need to interpret it in that way. What power of the base is the input of the log? If you have a calculator like this, you can use math, alpha, math. So what I did is I just pressed the math button, the green button, and the math button again. And it brings up this little thing for me to input. And I can put a 5 down here as the base, and I can put a 125 there as the input, and I get 3. Okay. If you're on paper 2, this will help you solve problems that have, no easy solution. So let me give you an example of that. Let's say that for some reason they were asking you to solve 2 to the x plus 3 equals 17. I don't know what power of 2 makes 17, and you don't know that either. Nobody knows what power of 2 makes 17 off the top of their head. So you go math, alpha, math, and you go log with a base of 2 and an input of 17 like that. To show your work, what you're doing is you are applying the inverse to both sides of the equation. Log base 2 on both sides. Log base 2 cancels the exponent base 2. So I get x plus 3 equals 4.087, so I'm going to round it to 9. It makes sense to me that the answer is a little bit bigger than 4 because 2 to the 4 is 16. So I know that I need to go to 2 to the something bigger than 4 to get to 17. And then the inverse of plus is minus. This is something that you know. So you get x equals 1.09. Okay? So when do you use a log? You use it when you're trying to cancel the base of an exponential in an equation. Okay? Logs are the inverse of exponential functions. Logs cancel the bases. And I want to go back and remind you that we do not use a log in this situation. If you have your variable as a base and your number as a power, then you just use a root. Okay? You only use a log when it's a number base and a variable exponent. Okay? One other thing that I should mention here before we talk about the graphs. There is a number that shows up a lot, and that number is e. The number e is not a variable. It's about 2.7. Kind of like how pi is about 3.1. E is about 2.7. E shows up a lot, especially when we're talking about population growth problems. So you'll often have an equation where you need to solve something like e to the x is equal to 5. Nobody expects you to know what power of 2.7 makes 5. You know it's about 2-ish. So the way you get that is you do the log base e of both sides, just like I did log base 2 in this example, just like I did log base 5 in my first example. I'm going to do log base e. But this shows up so often that we have a special button, ln. ln stands for log with a base e. ln has its own button on the calculator right down here, ln 5. ln stands for the natural logarithm. The reason the n and the l are backwards is because of French. They call it the logarithmic naturel. So ln of 5, 1.6-ish. Okay? So now let's talk about graphs. I'm going to try to clear everything out. We'll talk about graphs. Okay, we're going to go back and do our easy examples first. I want you to look at the graph. Here's the first example I gave, x plus 5. And then the inverse was subtracting 5. Okay, look at those two beautiful graphs. Then I did an example of equals x to the 5th power. And the inverse of that is the 5th root of x. I'm just going to write that as the 1/5 power, just to remind you of that. So there's definitely some symmetry going on here between an original function and its inverse. So let's look at our example of 5 raised to the x compared to log. Actually, I think I need to log base 5. Okay. I'll explain it in a second. Okay, so notice that I put the log 5 on the bottom. This is a little thing called the change of base, which is that if you have log base 5 of x, that is equivalent to log of x divided by log of 5. This is not something that you're going to need to prove on the SL test. It's just a true fact. Just think of it as the 5 is on the bottom on the left side, the 5 is on the bottom on the right side. They're just equivalent ways of writing a log. Don't worry about it too much. It's called the change of base. Okay, so what do we notice about every function compared to its inverse? I hope what you notice is that there is some sort of mirror image going on here. What you can see is that all of the functions and their inverses are mirrored. Here's another example. Let's look at y equals 3x, and then y equals the inverse of times 3 is divided by 3. Okay, so every time, why don't we just look at them one at a time? So you can see my original function and its inverse. You can see my second set of function and inverse. You can see the exponential function and its inverse. You can see the multiplication function and its inverse. All of these functions have a mirrored symmetry around the same line. If I type in y equals x, you can see that that is the crease. If I was able to fold all those graphs, they would line up on top of each other. So every function reflects over the line y equals x to be the graph of its inverse. Okay, now let's focus in just on the log. Think about what we know about our original function, y equals 5 to the x. If I look at y equals 5 to the x, the domain is what numbers can I plug in for x? And if I look at that, I can plug in any number. It just goes left, it just goes right. There's no stopping it going left or right. Some people write the fancy R to say all real numbers. Some people like to write it as negative infinity, comma, positive infinity, like that. Other people just write the words all real numbers. Every x value can be plugged in to 5 to the x. Now, let's switch that to the inverse. The inverse function is log base 5 of x. And so now, the domain of the original one got flipped over the line y equals x. So when I was talking about the x values of the original function, 5 to the x, now I'm talking about the y values of the inverse function. So instead of talking about the domain, I'm talking about the range. What this means is that the range of a logarithm is everything. And you can see that on the log graph. It never stops going down, it never stops going up. Its range is infinite in both directions. Now let's switch gears and talk about the range of the exponential function. The exponential function has a horizontal asymptote. It never goes below the x-axis. So the range of 5 to the x is everything from 0 up to infinity. And it never reaches 0. You can never multiply a number by itself and end up with an answer of 0. You can never multiply a non-zero number by itself and end up with an answer of 0. And so then that switches when we think about the inverse function. The range of the original function is the domain of the inverse function, 0 to infinity. And so that means you can see that there is this vertical line that my logarithm never crosses. My logarithm starts at x equals 0. It doesn't quite touch x equals 0, but it goes to the right from x equals 0. Okay? So everything that you know about exponential functions, you just need to switch x and y, and then you will have the corresponding facts about your logarithm functions. Okay? So what I'm going to do next is talk about properties of exponents and the properties of logarithms, and then we'll finish up talking about transformations of both of those. Okay, so here are your exponent properties. These should be somewhat familiar to you. If I had something like 2 to the x times 2 to the y, I can make that 2 to the x plus y. The 2 is not important. It could have been 5 to the x times 5 to the y. It could be 7 to the x times 7 to the y. As long as the base is the same, you can add the powers. And similarly, if I did 7 to the x divided by 7 to the y, I'd make that 7 to the x minus y. If I had e to the x raised to the y, I could make that e to the x times y. Okay? And if I had x times y raised to the 5, I can make that x to the 5 times y to the 5. So those are the things that you should be familiar with when we're talking about properties of exponents. Okay. This one what we're going to do is remember this inverse idea. What does an inverse do? It switches the x's and the y's. It switches the inside of the function and the outside of the function. Switches inputs and outputs. So I'm going to write this same rule in terms of logarithms. So what we can say is that the log base 2 of x times y, I'm going to give myself a little more space. I always think I can squeeze it in, but then I never can. All right, let's try this again. So we've got, where's my pen? There it is. So we got log base 2 x times y becomes log base 2 of x plus log base 2 of y. It's the same idea. When you're multiplying two things, you can add the exponents. And so if I'm taking the log of two things multiplied, I can add the two logs, because the log gives you what the exponent was. Very similarly, if I have the log base 7 of x over y, I can make that the log base 7 of x minus the log base 7 of y. This one's maybe a little bit weirder for people to see, but if I have y times the natural log of x, I can make that the natural log of x raised to the y power. Okay. So those are the three main log rules that you're going to need to use, and sometimes you might need to use more than one in a problem. Okay. So last thing I wanted to talk about in this video, and in a separate video I'll do a few examples, is looking at the transformations of the graphs. So let's look at our original graph, y equals 5 to the x, and then let's transform it. So let's say I had a new graph that was y equals 2 times 5 raised to the x plus 1. And then plus, let's go minus 3. What did each of those do? Times 2 made it twice as tall. It's a vertical stretch of 2. The plus 1 made it one step to the left. And then the minus 3 made it 3 steps down. And you can see that that's what happened with my black graph. Okay? What I'm going to do is show you how you could find the inverse of that transformed function and what we can predict the graph would look like. So remember, inverse means you switch x and y, and you solve for y. So I'm going to add 3. I'm going to divide by 2. How do I get rid of the 5 base? I do a log base 5. So I do a log base 5, log base 5, x plus 3 over 2. Last step, minus 1. And that's the inverse. So what does that do? Well, instead of going down 3, it goes 3 to the left. Instead of getting twice as tall, it gets twice as wide. Instead of going one step to the left, it goes one step down. Because all my horizontals and verticals switch when I am looking at the inverse function instead. So I'm going to type this in just by using that change of base idea. So I got log x plus 3 over 2, then log 5, just to get it to be a base of 5, minus 1. And you can see again that that is a perfect reflection over the line y equals x. And you can see that it obeys those same rules of shifting down 1, 3 to the left, and getting wider compared to my black one that shifted 1 to the left, 3 down, and twice as tall. All right, wonderful. So that was just kind of overview of everything from logs. If you think of something else, please let me know and I'll help out. In another video, I'll do some examples.